Hi everyone, my name is Ivan Grohodkov. I am VP of Software Platforms at Espressif. My talk is about developing, publishing and maintaining components for ESP-IDF. In ESP-IDF, applications are built from components. Some components are part of IDF itself, some are developed as part of the application, and many additional components can be found online, published by Espressif and by the community. Last year, we have introduced IDF Component Manager, which is a tool that simplifies downloading and installing components, as well as sharing components with other developers. In this talk, I will explain the best practices that we at Espressif recommend to component developers. And after watching this talk, you will get familiar with the process of creating a component, adding examples, tests, and documentation, publishing it to the component registry, and setting up the workflow to simplify maintenance and contributions. I have many links to documentation and reference pages inside the slides, so if you would like to follow along, there is a link to the slides over here. You can also scan the QR code to open the link. The plan is first to take a look at developing the component, go over the structure, adding source code, examples, tests, and other basics. Then look at publishing the component and publishing the documentation. And finally, go over some maintenance topics related to CI and also managing contributions. For illustration purposes in this talk, I'm going to use a very simple component that I have developed. It's a driver for a PA1010D GPS module. The GPS module does have a UART interface for which you don't need any driver, but it can also be used over I2C, and this component provides a driver for that. The repository of this component is on GitHub. Again, you can scan the QR code if you like to follow along during the presentation. And the second link is the page of this component in the component registry. To start with, let's create the component. For this, I'm going to use IDF PyCLI tool, which has a create component convenience commands. This component creates a simple boilerplate with a project CMake list file, one source file, and one header file. And we will just have to put the component code in. The source code of the driver is not really the point of this talk, so I will not spend much time here. We have a header file where the API of the driver is defined, just 3 simple functions, and the source file where those functions are implemented. Essentially, we're just reading 1 byte at a time from a specific I2C register and wrapping it all in a simple API. While writing the code, how do we actually compile and test it? In ESP-IDF, the build process always starts with the application. So to test this component, we will have to create an application. Typically, this is either an example or a test application. And we'll use one of those for our compile run debug cycle. In the case of examples, I recommend placing them into the example subdirectory of the project. The component manager actually looks for example projects in this subdirectory and makes those examples available for installation in addition to your component. You can also use some other directory, in which case you will have to customize this, the name or the location of the examples. We will take a look at how to do this later. And for the test apps, they can be under the test apps subdirectory. This name is just a convention used in ESP-IDF. You can also pick something different if you like. I'll explain more about the test apps in a later slide. For now, let's start with the example project. Again, I'm going to use IDF PyCLI, this time the create project command. And once the project is created, I'm going to go inside the project and build it just to make sure that the project itself is okay. The structure is very straightforward. Inside the component, we now have this example subdirectory, and there is a single example with the source file and CMake. So here is the example boilerplate. We see that there is just an empty app main function. Again, we will have to put some code inside. One thing to note here is that actually when we have compiled this example, it didn't compile the PA1010D component, which this example is part of. To do this, to compile this PA1010D component, we will have to add a dependency. To add the dependency, we're going to create an IDF component YAML file. And the IDF component YAML file is going to be here inside the main component of the example. IDF component YAML file is the manifest file for IDF Component Manager. It can be used for two purposes. One is to describe the component, and we will do this later when we will be adding the manifest file for our component. Another case is for adding dependencies. In this case, we are specifying that there is a dependency on the component. IGRR is the prefix in my namespace in IDF Component Manager. This is the component name. In this case, I'm not. It doesn't really matter which version of the component we are installing. So this actually adds the dependency on this component. And one other thing we have to do here is that for local development, we have to specify the override path. What override path does is that if IDF Component Manager can find the component, in this case 3 directory levels up from IDF Component YAML file, then it will use the local copy of the component and not download the copy from the IDF Component Registry. This is something we do want when working on the component itself, because we want to be able to make changes to the component source code and see them being reflected in the example immediately without having to upload everything to the component registry and then download it again. And this is achieved by specifying this override path. After we have added dependency on the component, we can actually modify the example code. So in this case, in the source file, I'm adding the include for the header file of the driver. Then there is just a simple app main which initializes the I2C driver, and then I'm initializing the P810D driver, and finally there is a loop where we're just going to be reading the NME message from the driver and printing the message to the console. So now that we have everything put together, let's try to build and run the example. We were going to run IDF PyFlash monitor, so the example should be built pretty quickly and then flashed to the device. And as we see, the example runs and it's printing some GPS messages that are obtained from the GPS unit, so everything seems to be good. All right, we have added the example. The example works. Now we can take a look at the test application. There are several things that we are commonly doing in test applications in ESP-IDF. First, we can run Unity unit test framework and run tests on real hardware. The next thing is we can use Linux target in ESP-IDF and run tests on the host. In this case, when you have some hardware dependencies, typically you're going to use mocks to simulate those dependencies. In the case of our component, we could mock the I2C driver to emulate the data that GPS sends over I2C, or maybe test scenarios when I2C operation may time out. Another thing we can do in test apps is to run some more complex integration tests. Depending on what your component does, this might involve, for instance, some form of network communication between the host and the device. And of course, you can have multiple test apps. For example, you can have a unit test app which runs on the host, and another app which is an integration test and it runs on a real device. Later in the talk, we'll take a look at the tools that are available to execute those tests in CI. Let's look at what else can be part of the component. We have already added CMake lists, source files, and header files. We've added an example application, and we could add a test application. Documentation is something we definitely will add, and we're going to take a look at this at the end of the talk. We will have to add IDF component YAML file to the component itself to describe what the component is and optionally declare dependencies on other components. If the component has some compile time configuration, then we can add a kconfig file, and then if we are going to rename any kconfig options for backward compatibility, we can add sdkconfig.rename file. Linker fragments can be added to customize placement of functions or data into RAM. And last, we can add software bill of material manifest. Software bills of material is a relatively new feature that has been introduced in ESP-IDF. And you can add the manifest for SBOM into the component as well. So overall, these are the typical things which can be part of the component. Now let's take a look at adding the component manifest. The manifest should be in the component directory next to the CMake list file. Here we can take a look at the component manifest that I've already written. We are specifying the version of the component. This is not mandatory. We have other ways to set the version, which we'll take a look at a bit later. We're specifying the description of the component, which will be mentioned prominently in the IDF Component Registry next to the component name. Some links to show the users where they can find more information about this component. The maintainers, the dependencies. In this case, this driver doesn't have dependency on any other component outside of ESP-IDF, so we are only specifying the constraint that IDF has to be above 4.4 because I'm using a certain API which was added in that version. A bit later I will show how we can handle compatibility with more IDF versions in the component. After we have added the component manifest, it's now a good time to also make sure that we have the component repository set up. So the minimal things we have to do here is to add the README MD file with the information about the component, which will serve as a homepage of the component. We can explain what the component is, how to use it, and any other important information. Then we have to add a license file. It's mandatory if you're uploading the component to the component registry. If you're maintaining private component, for example, within your company, you don't have to add a license file, but keeping it there might be a good idea anyway, even if to specify that this is proprietary code and not to be shared. And finally, we have to make sure that everything is in some version control system. In this case, I'm using Git, so I have added all the files in the repository into Git. And now that all those things are in place, we can actually upload the component to the component registry. First, we're going to do this manually, and then we're going to set it up in CI. So the steps are going to be fairly simple. We're going to sign into components.espressive.com, then log into the registry in the CLI. Then we can use compot component upload with the dry run flag to try to perform the upload without actually creating the version in the registry. So this is just a validation step. And then we're going to use compot component upload to actually create the version. Once the component is uploaded, we can go to the component registry and see the result. Let's take a look at how this works. So first I'm using compot component registry login that gives me a token which I input in the CLI. In this case, this is a token with a short expiry time, so it's already invalid, but you should keep your tokens secret. And now that I have the token, I can run compot component upload with dry run argument. As we see, the process succeeds, no issues. So next step, I can run compot component upload without dry run to actually create the release in the component registry. And I've done this in the meantime, and we can take a look at the result. So on the left is the manifest that we used, and on the right is the page in the component registry. We see that all the fields that we have specified in the manifest, they are reflected in the registry. The version, the description, the links, the maintainers, the license has been extracted from the license file. We only have a dependency on ESP-IDF, which is listed here. As you see, the example that we have added has been detected, and the information about this example is available. And the rest of the page is the README file of the component, the root README, and if we were to add a README file in the example, there would be an example as well. All right, so we now have the component successfully uploaded. Let's take a look at another example of the manifest for some more fields that we can specify. This is IDF component YAML file from ESP-DSP project. And in this case, one additional thing we see is that if the example application is not under the examples subdirectory, as I showed before, we can actually tell the component manager where to look for examples. In this case, in ESP-DSP, they have additional apps under the application subdirectory, so we can specify the path over here. Also, we can exclude some files from uploading. For example, if you have large files, or if you have some files which are just not necessary for using the component, then such as maybe tests or some CI related files, you can exclude them and then they will not be uploaded to the component registry. For more fields that can be specified in the component manifest, such as target, version, and so on, you can check the reference link over here. One thing that we looked at before was that I have added the version constraint for ESP-IDF to the component. So I have specified that the component only works with IDF 4.4 and later. If I wanted to make the component compatible with more IDF versions to make it easier to use, I could use one of those methods to achieve compatibility. So in IDF component YAML file, we can use rules if we need to make a dependency on certain other components configurable depending on the version. In the build system, I could add different source files or different compile definitions depending on the IDF version. I could use those IDF version major or IDF version minor macros. In this case, if I wanted to make the component compatible with IDF 4.3, I could add a file that would be compiled only for that revision, and that file could provide maybe the missing functions that have been defined in IDF 4.3. And in source code, I can use ESP-IDF version or ESP-IDF version val macros to guard some pieces of code. For example, if there is a structure member that was added in a subsequent release. So using these tools, you can make your component compatible with more versions of ESP-IDF, and therefore it will be easier to combine it with other components. One thing I want to mention here is that the repository layout that I have described so far is not the only one possible. It is a recommended layout, but if you already have a project and you have a certain repository layout, you don't have to change it just to publish the component in the component registry. I will show two examples here. The first one is similar to the layout of LVGL project. In this case, you may already have source files and include files in specific locations in the repository. And if you need to add support for ESP-IDF and publish into IDF Component Manager, then you can keep all the IDF related files in a subdirectory. In this case, you may have some maybe IDF specific port layer, the IDF component YAML file, and a CMake file. And if you wanted to add support for Zephyr, for example, for your project, then you could add a Zephyr directory here, also add Zephyr module YAML file and a Zephyr port file. And in the root CMake list file, depending on the environment, you would include either idf.cmake or zephyr.cmake. So this way, your repository layout stays the same, and you can add the IDF functionality in a subdirectory. In this case, when you're uploading the component to the component registry, you just need to copy this YAML file to the root of the repository. The other approach we can take a look at is similar to that used in ESP Wolf SSL component. In this case, there is the upstream project, in that case Wolf SSL, that is added as a submodule. So we have an upstream repository that is not modified for IDF support, and then there is a wrapper repository where we actually add the CMake list file, IDF component YAML file, and if necessary, some port-specific source files. When the upstream project makes a new release, you update the submodule commit in the wrapper repository, increase the version in IDF component YAML file, and make a release as well. So with these two approaches, you can keep the repository layout, and you can still add support for ESP-IDF and publish into IDF Component Manager. All right, let's recap what we've done so far. We have created the component, we've added an example, a test application, we created the manifest, and the first version has been uploaded manually. Now, remaining part of the presentation, we will take a look at versioning the component, how to handle private components that we are not publishing to a component registry, and we're going to take a look at CI related things such as uploading releases automatically, running some testing in CI, and finally we will cover documentation and contribution management. So first, let's talk about versioning. IDF Component Manager uses a versioning scheme that is an extension to semantic versioning. Just like semantic versioning, there are three version components, major, minor, and patch. There is an optional pre-release part, and the extension that we have in the IDF Component Manager is this revision component. Let's take a look at some of the examples. 1.0.0 is a valid semantic version. It's also a valid version for an IDF component. In this case, it would be a release version. 1.1.0 RC1 would be a pre-release version. And the last two examples show that revision field. This is mainly used in the case when we have an upstream library. The upstream library might have some semantic version, in this case 5.2.3. And we might be publishing this upstream library in IDF Component Registry. If we want to distinguish some changes that we have done, for example, in the port layer or in CMake file or in kconfig file, we may want to do multiple releases, and to distinguish between those releases, we can use the tilde character and the revision number. So this syntax can be used if you have some upstream library that you need to publish. So now that we know what the version is, let's take a look at where to store the version. There are two cases here that I want to cover. The first scenario is the simplest one. If we have a repository with just a single component, like we have in our example with the PA tent and GPS driver, in this case I would recommend using git tags to identify releases. This is the most straightforward option for developers, as it's always easy to find where exactly the git tag is pointing to. If you store the version in git tags, it's not necessary to add it in the IDF component YAML file. You can keep it there, but in this case you will just have to make sure that whenever you make a git tag, you also update the version in IDF component YAML to match the tag, and this is just extra work you have to do. So the simplest solution is to not specify the version in IDF component YAML file, and instead tell the component manager to get the version directly from Git. The second scenario is when you have a repository with multiple components, like a monorepo. In this case, most likely these components will not share the same version, and you will have to keep track of the version of each component somewhere, and that place will probably be IDF component YAML file. In this case, the recommended approach is to try to upload a new version of the component on every commit. The compot component upload command has an allow existing flag, which tells the component manager that if the component version has already been uploaded, it will not do anything. So it will not override the existing version. And it will only upload the new version if that version doesn't exist yet. So this way, when you make a commit which changes the version number in some component, CI job will automatically upload the version to the registry. For these two use cases, we have a couple of examples. The first approach is illustrated in ESP-32 camera repository, where there is no version field in IDF component YAML file, and versioning is done using git tags. And the monorepo approach is illustrated in IDF extra components repository, where there are multiple components and each component has its own version specified in IDF component YAML file. One more note, you can actually fully customize how you store component version. If the component version comes from some other place, let's say from some header file, you don't actually have to duplicate the version in IDF component YAML file. You can extract it from the header file and then pass it to to compot component upload command. In that case, version management is completely up to you. One side note here is about private components. Not every component that will be developed for ESP-IDF would be publicly available. You may be developing components that will be used just within your company. In this case, you can keep the component in a private Git repository, and you can specify where the component, where to download the component from using this Git reference in IDF component YAML file. This allows you to add dependencies on components that are only available, for example, within your company. And this way you can build a library of shared components within your team without publishing them to anyone else outside. Note that even though some components in your project would be private, you can still combine them with other components from the component registry. So let's take a look at the example. In this case, we have three dependencies. The first one is the libpng library from IDF Component Registry. The second one is a dependency on a Git repository. In this case, it actually is a public repository, but this component just hasn't yet been published to the component registry. And I'm adding it as a Git dependency. And the component actually is located in a subdirectory of this repository. And the third case here is local dependency. In this case, I'm adding the dependency on protocol examples common component that is located within ESP-IDF project. The behavior here would be exactly the same as if I were to add this component using extra component dirs variable in CMake. So as you see this way, you can add dependencies from different sources, and they can all be combined within the same application using the IDF Component Manager. Now let's get back to our main topic. Previously we have uploaded the version manually using compot component upload command. So now let's do the same thing automatically in CI. For projects which are using GitHub to host their repositories, we provide a GitHub action called upload components CI action. And you can add this action to your repository by creating a workflow file similar to the one we have here. The logic is very simple. We check out the component using the checkout action, and then we use this upload component CI action specifying the namespace, the component name, the version. In this case, the workflow will run only for Git tags, and we are taking the component version from the tag name. And the component API token is the same token that we used when we were uploading the component locally using the CLI. If you are not using GitHub to host your repositories, for example, you might be using GitLab, then you can use the IDF Component Manager Python package directly. So you just need to have some environment where Python is installed and install the IDF Component Manager package, and then use compot component upload command, same way as we did this in the CLI. In this case, again, I'm specifying that this workflow should only run for tags, and then I'm passing the tag name to compot component upload command so that I don't have to keep track of the versions in IDF component YAML file. If you're using a different CI/CD system than GitLab, then it should be very similar. You can use the same command there as well. Now let's move on to testing the component in CI. It's an important part of development and maintenance process, and we can take a look at the things that we can do in CI to test the component. Compilation checks are the simplest type of testing. We essentially just verify that the component builds. This can be used if you, for example, have some kconfig options and you want to verify that the code can be successfully compiled with different values of those kconfig options. You may also want to run compilation checks to verify compatibility with different IDF releases. The other thing you can do is you can run static analysis, for example, using a tool such as clang tidy. And you can run unit tests either on the host or on the real hardware, like a development board, or on the emulator. And you can run integration tests again in an emulator or on a real hardware. Let's look at those one by one. So for compilation checks, for projects that are maintained on GitHub, again, we have a CI action called ESP-IDF CI action. In this case, we define the build matrix. We can build the component for all combinations of those releases and the chip targets, and we can specify some additional releases and chip targets this way. We are using the checkout action again to get the source code, and then ESP-IDF CI action specifying the version and the target, the chip target to build for. Those come from the build matrix, and if we have multiple examples, we can invoke this action multiple times, specifying the different example path that needs to be built. So this is very easy to set up. There are just a few lines of code that you need to add to your repository. The downside is that this approach doesn't scale well if you have to build multiple applications or multiple configurations of the same app. So you will have to repeat this several times for different apps in your repository. In this case, there is a more comprehensive solution called IDF Build Apps. IDF Build Apps is a tool which can recursively find and build IDF applications inside a repository. It can build for multiple chip targets, it can build for multiple app configurations, and there is a configuration file that you can use to customize very flexibly the build matrix that is going to be generated. IDF Build Apps also knows about parallel builds. In this case, in this workflow, I am defining a matrix with multiple IDF releases and multiple parallel builds, and using the IDF Build Apps package to find all the apps in the repository and then build them. IDF Build Apps will automatically split all the work that needs to be done between multiple CI jobs. If your project has high enough complexity, so if you have a larger number of test apps, then this is definitely an approach to go for. The downside is that in this case the workflow is slightly more complex. You have to maintain some configuration file and so on. So now looking at unit and integration tests. For running unit and integration tests, we recommend using PyTest with PyTest Embedded plugin. PyTest is a testing framework for Python code, and PyTest Embedded is a plugin for this framework that allows using Python to write tests for embedded applications. PyTest Embedded runs on the host PC, and it controls the test application that runs on the embedded device or inside the emulator. PyTest Embedded can find the applications that have been built, for example, manually or using IDF Build Apps. It can flash the application to the device over a serial port or JTAG. It can send input to the application. For example, if your app needs certain console command to start the test cases, and then it checks the serial output for specific conditions. For example, if your application is printing the number of passed and failed cases, you can expect that in this case you actually get 0 failed test cases. And you can also specify regular expressions and other things. And the nice thing about PyTest Embedded is that with the same test case, you can use the same test case to run on real hardware or on the emulator, and both locally and in CI. For more details about PyTest Embedded and using it in CI, please take a look at the talk called Streamline in Development with CI/CD, which we have here at the DevCon. The next step, running static analysis. Aside from compilation checks, we can use CLang Tidy Static Analyzer, which can reveal more potential problems with the code. And CLang Static Analyzer integration is achieved using this IDF Py CLang check command. In CI, we can run IDF Py CLang check. It's going to produce a list of warnings, and then we can convert those warnings into one of the report formats depending on the service we use. And then that report format can be uploaded to the repository hosting. You can take a look at this example we have here in IDF Extra Components. The workflow for adding IDF CLang Tidy Check is fairly simple, and it integrates very nicely with GitHub code scanning. In the beginning, I mentioned that we will talk about documentation. Depending on the component you're developing, you can decide what documentation you need to provide to the users. There are typical types of documentation you can consider creating. Reference, basically documenting each function and each data structure your component provides separately. Explanation, so in-depth, detailed explanation of how those functions have to be used together. And you can also write tutorials and how-to guides. For IDF components, we recommend the following approach for minimal documentation that you will provide. For the reference part, we recommend documenting the APIs in a header file using Doxygen comments. We can use Doxygen together with a tool called Doxybook to generate the markdown file, API-MD, and in this file there will be a nicely formatted API reference. then you can write explanation part in either in readme.md or inside a top-level file comment in your header file. Once you have readme.md and API.md in your component repository, the component registry will automatically render the documentation in the README and in the API.md in the page of your component. So let's take a look at what this looks like for our example component. I have documented the component API in the header file using Doxygen comments, added a doxy file, which is a configuration file for Doxygen, and generated API.md using Doxygen and Doxybook. In readme.md I have the basic description about the component. So on the right we can see the page of the component in the component registry, and over here after the readme file you see that we actually have the API reference part. This comes from api.md, and this part is generated from the Doxygen comments we have added in the header file. So if you want to add some more detailed documentation of one of the functions, then you just need to update the header file and then regenerate API.md. One nice way to do this is using pre-commit hooks, and I will mention about pre-commit hooks in the next section. So finally, let's take a look at things we can do to streamline contributions and help contributors bring useful changes to your repository. I would recommend adding contributing.md file to the repository, where you specify your expectations for other contributors, and you can also use this file to keep some notes about how the development of the component should be happening. So is there anything specific that needs to be paid attention to in when opening the pull request? How do we run test cases? Are there any code formatting or commit message guidelines? What's going to be the release process, and so on? Adding GitHub pull request and issue templates, or GitLab issue and pull and merge request templates is a nice touch as well. Enabling builds and tests and PRs can help you spend less effort when someone opens a pull request. You can rely on CI to automatically validate the changes. And one additional thing that I recommend adding is pre-commit hooks. So pre-commit is a script that Git runs when making the commit, and pre-commit is also a framework that simplifies adding Git pre-commit hooks. To use pre-commit in your repository, you can add a pre-commit config YAML file, and in that file you specify the types of checks that you want to perform with this commit. During the development, developers need to install pre-commit one time, and then when they run the commit, the checks will be performed automatically. If some checks fail, usually the code will be fixed automatically as well. For instance, maybe the code will be reformatted or line endings will be fixed. The developer can then review the changes that were done by the pre-commit hook and stage them, and then run the commit again. It is also nice to add a CI job that will actually verify that developers have installed and run pre-commit. Here is an example of pre-commit from one of our repositories. In this case, we have some standard checks for line endings and other simple checks, and also code formatting, C code formatting using A-style. So with this pre-commit configuration, you can very easily make sure that all contributions to your project will be uniformly formatted. All right, we are at the end of the presentation. Here is the checklist of things that you can consider doing when you're publishing a component to IDF Component Registry. For the final result, please take a look at the repository over here and at the page in the component registry, which is the final version that we have achieved by following all those steps. I hope that this talk was helpful to you, and it will simplify the process when you need to publish a component in the component registry. Thank you for your attention, and I will be taking your questions.